Hi students, today we are going to discuss about the solubility of solids and liquids. Okay, so can you give some examples for solids and liquids? So far we have discussed many number of solvents all coming under this category of liquids. So if you take some examples for solids, okay, some as a pharmacist you know that aspirin, right? Some of the solids we can say that there is a solid tablet, or common salt is the another best example for solid. So when we are adding those solid compound in the liquid or in the given solvent or in the given liquid, the solubility will be happen or the solution will be prepared, and the process is called solubility. Okay, so today we will talk about the solubility of solids in liquids more detail. Okay, so what is solubility of solids in liquid? So solid in liquid solutions are considered as an important class in the pharmaceutical solutions, as of course, because in the drug discovery process the solubility is very important. Particularly we are handling number of solid compounds. In an ideal solution, particularly if we deal about the solids and liquids, the solubility of solids and liquids is influenced by the several factors such as temperature, melting point of solid, and molar heat of fusion. These three components are important for the solids and liquids, and particularly for to make the ideal solution. Okay, so the next is nature of the solvent does not influence the solubility of an ideal solution particularly, but this is not the case for real solution or non-ideal solution. Okay, for an ideal solution, the heat of solution and heat of fusion, okay, that means heat of formation of solution and heat of fusion of the solid molecule all are equal, particularly for ideal solution. In non-ideal solution or real cases or real solution, so what compounds are called non-ideal solution? Whichever or whatever the solutions or compounds not following the Raoult's law, those solutions are called as non-ideal solution or real solution. Those activity coefficient termed as gamma 2 is influenced by the nature of solid solvent and also by the temperature of the solution, because the nature of solid is important, nature of solvent is important, the another factors, external factors, temperature is also important. Okay, so gamma 2 is nothing but activity coefficient is a factor used in thermodynamics particularly to account for deviations from ideal behavior. Okay, so the next concept is dissolution. Dissolution is almost equal to the solubility, but this is a little bit different terminology. Particularly this is useful for kinetics. That means to find out the rate determining, for that purpose in solubility we are using the dissolution concept. What is dissolution? Dissolution refers to the process by which a solid phase goes into liquid phase. Okay, in that such as water as an example solvent, that is nothing but mass transfer of solid into liquid, that is the dissolution. That means if you have the add amount of solid particles into the liquid, in that solid particles one or few particles of the surface of the solid particles are enter into the liquid and gone for making the solution, or it's dissolved in the given liquid. This is called dissolution. Dissolution is the rate determining step for hydrophobic and also poorly aqueous soluble drugs. Hydrophobic means what is that? It is not accepting the water, it's not highly interacting with the water. Hydrophobic interactions, hydrophobic solutions, and wherever the solubilities are very poor, for those drugs the dissolution is the important concept to determine the rate. What is the rate? So in 1 minute or in the particular seconds or particular given time, how much amount of solid particle dissolved in a given solvent or liquid, that is the rate or determining step, which is the focus point, which is the determining point for our designing a place to make sure the solubility is happening. okay, and also how fast the solubility is happening. We can speak in terms of rate determining step. We can get to know more details from the rate determining step, that is nothing but kinetics. Okay, so here I just represent a picture. Over here I shown a picture. This is the solid particles, and you see here the next picture, the removal of surface. One of the particles from the surface is moving out into the solution. Okay, here entropy and enthalpy will change and enter into the solvent. The solvent create the space for the incoming solid particle and make a solution. Okay, so this is called dissolution in the given time using the various factors. Okay, this is the second slide. The bottom picture clearly shows solvent create the vacancy, create the place for the incoming group, or create the cavity for the incoming solid particle to make a solution. What is the importance of this dissolution? So these dissolution are useful for the determine the quality of pharmaceutical dosage forms and select the proper drug candidate for formulations. Okay, purity is important, and the second is to select the proper drug candidate for formulations. These are the two main importance of the concept of dissolution. What is dissolution and solubility? What is the difference? You can see here, dissolution is a kinetic process, right? Rate determining step we can find out by using this dissolution process, and as a quantified by its rate. Yes, in the given time, how much the rate, how much speed of the solubility will be happen. This is using the dissolution we can speak. It is the transfer of mass from solid phase to a liquid phase. And also the dissolution rate refers to the rate at which a solid dissolves in a solvent at given time. In 1 minute or 30 seconds, how much solid particles are dissolved in a given solvent. Okay, if you come to the concept of solubility, solubility quantifies the dynamic equilibrium state achieved when the rate of dissolution equals the rate of precipitation. The rate of dissolution equals the rate of precipitation is called solubility. Solubility is a chemical property referring to the ability of a given substance, the solid, to dissolve in a given solvent. Okay, this is a chemical property, the solubility is. Discuss about the factors affecting solubility. What are the factors affecting the solubility as well as the dissolution? The parameters are temperature, agitating solution, increase surface area of solid, increasing surface pressure. These are the four important parameters which will affect the dissolution rate as well as the solubility of a gas as well as the solid. Okay, so here we will see that first parameter for the dissolution, the temperature, if we increase, that will dissolution of rate also increase, and agitation increase, dissolution of rate will increase. Increasing the surface area, the dissolution rate will increase, and if you increase the surface area pressure, there is no effect on the dissolution rate. But when you go for the solubility, if you increase the temperature, the solid particle solubility will increase, but gas is opposite, that will be escaped from the surface and it will go for the freedom state because of the entropy change, and solubility will be decreased. Agitating, if you disturb the solution, there is no effect for solid, but the decrease will be happen for this solubility of a gas. The third component, increase surface area of solid, then dissolution rate of a solid increase. Okay, but if you go for the solubility of a gas, there is no effect as well as the solid. The fourth point, increasing surface pressure. In the solubility of a solid, there is no effect. Even increase the pressure also, there is no effect. But if you go for this gas, if you increasing the surface pressure, the solubility of gas, what will happen? If you are increasing the pressure, then solubility of gas will be increased. This is the factors affecting solubility parameters. Okay. Next, factors affecting solubility, the first one is temperature. We will see in detail. In general, temperature increases the solubility of a solid that dissolves with absorption of heat, that is the accepting the heat, then it will be dissolved, more amount of solid particle will dissolve, that is endothermic process. So as per the Le-Chatelier's principle, when a system experiences disturbance, from the outside because of the external factors, external parameters. If you realize the disturbance, then it will respond to restore a new equilibrium state. It will not stay in the same equilibrium state as per the Le-Chatelet-Perron principle, such as if you change the concentration, if you change the temperature, if you change the pressure, then that equilibrium state will be shifted and it will maintain or restore the new equilibrium state. Okay, then change in the concentration. If you add more amount of reactant, that is the concentration, right? If you are adding the more amount of solid particles, then concentration amount will be increased. That means concentration of the solution will be increased. If you add more reactant or more solid particles, the forward reaction will proceed and will reach the equilibrium. Here the first equation is talking about the A to U, which is maintain the equilibrium. Okay, the delta H is minus 100 kg and the second kilojoule per mole. The second one is A, we are applying the heat or we are giving the heat plus A, then it producing the B and also set up the equilibrium. The first case is the heat is liberated, the reaction is called exothermic reaction. The second one is the heat is accepted, that means taking the heat during the reaction and producing the product of B and maintain the equilibrium. Then the value of delta H enthalpy is 100 kilojoule per mole. So this process is endothermic process, right? Okay, so another one is factors affecting solubility, which is particle size. If you have the small size, the solubility is easier. If you have the big size, it will take time because you need to break the surface and we have to come inside the surface and make it the complete solubility. The particle size is very important. So the size as well as the surface affects the solubility. If it is a very hot surface, then it is very difficult for this solvent solute interaction and it will take long time for the solubility. Generally, solubility increases with decrease in particle size, right? If you have a small particle size, the solubility is very easy. If you have a big particle size, the solubility is quite difficult. Okay, so which results in excess surface energy, it will increase in surface area. So there is a small particle size, that is interaction with the solvent is easier and the solubility will become very easy. The next equation relating the solubility and size. What is the equation? Log S by S0 is equal to 2 gamma m by 2.303 RT rho R. So what is S? Solubility of fine particles, S0 is solubility of relatively large particles, gamma is surface tension of the particles and R is the radius of fine particles. The rho is density of the solid, R is gas constant, T is the absolute temperature. Okay, so here the particle size, there are the symmetric particle and asymmetric particles also possible, right? So symmetric particles maybe take long time, that means less soluble in the given solvent than unsymmetrical particles. Why? That symmetrical particles are arranged in the proper way. Then it is very hard for that to break the covalent bonds or the ionic bonds on or the other cohesive forces existing in this symmetric particles will take long time for the solvent. But unsymmetrical particles is not such case because it's not arranged properly, so is breaking the cohesive force by the external solvent molecule is easy, so easier. So that solubility of unsymmetrical molecule is so in dissolve in the given solvent is easier than the symmetric particles. Okay, so this is about the particle size, that is one of the factors which are affecting the solubility of the solid in liquid. Okay, the next one is solvent is also influencing or affecting solubility. What is the effect? What are the effects of from the solvent? The solubility of a solid depends on the nature of the solvent. Of course, if you are taking the polar protic solvent, the polarity nature is high, then it's easy for the solubility. If you take the non-polar, then you have to look into only the solid particles. Non-polar solid particles only possible to dissolve. Okay, so polar solid dissolved in polar solvent. That means like dissolves like, polar dissolves polar, non-polar dissolves non-polar. That is the major concept in this solubility. Okay, the next one is increase the solubility of poorly soluble substances by use of more than one solvent. If I have the solvent and solute, I am adding the solute into solvent, the solubility is taking long time, or it is not immersible. Then what I can do, I can bring the third component as another solvent to help for this solvent to solubilize the given solute molecule. Then the second part of the solvent is incoming solvent, or we are adding the extra solvent, is called co-solvent. The process is called co-solvency. Co-solvency is always help for the solubility whenever the solid particles are facing a problem to dissolve in the given solvent. Okay. Then another factor is pH effect. Most of the drugs are either weak acids, which is in general are less soluble in water. pH effect, particularly most of the drugs are weak acid. Yes, it is initially not dissociated. After entering into the body, the molecules or the drugs are dissociated. That's why most of the drugs are weak acid. Okay, these things are less soluble in water. The solubility influenced by pH. So whenever the drug molecule enter into our body from the mouth to this GI, gastroenteric, then the solubility will increase and depends on the pH, because in every places the pH will differ until to reach that our GI tract or to reach the particular target. So the pH effect is very much important and playing important role in the solubility. Adjustment of pH, that means fine tuning the pH to an optimum value, may be necessary to obtain a clear homogeneous solution of drug substances with maximum therapeutic effectiveness. So pH fine tuning is essential for increasing or to increase the solubility. Okay. The next, solubility of slightly soluble electrolyte. If the given electrolyte is very much less soluble, what we have to do? So addition of a compound bearing a common ion reduces the solubility of sparingly soluble. Already the solubility is very low. We are adding that another ion into the solution, again the solubility will go down. For example, sodium chloride is there, it is very much difficult to dissolve in the given organic solvent. Then we are adding this another KCl. Here the incoming group is also having the chlorine ion. Here existing component is also chlorine ion in the sodium chloride. Incoming group have that chlorine ion in KCl. So these two chlorine are same ion. If you enter into the solubility, the two chlorines, that means the ions are common, then it reduces the solubility. It is called common ion effect. Okay. Then effect of non-electrolytes. Non-electrolytes, glucose and sucrose, those things are example for non-electrolytes on the solubility of electrolytes. What is the role? The electrolytes dissolve in water because dissociation is happening, right? So dissociation of the dissolved molecules. This dissociation is influenced by the dielectric constant. Now, electrolytes have the huge dielectric constant of the solvent, and if a water soluble non-electrolyte such as alcohol is added to the aqueous solution, this effect is due to the lowering of dielectric constant. Okay. This is the effect of non-electrolytes on the solubility of electrolytes. Okay, the next concept is surfactants. So you can see that picture is like coronavirus, right? You can see this. This is like a ball and many kind of head man or sitting or standing on the wall like a pin kind of things, right? So here the surfactants is have the two kind of tiles and heads. So heads and tiles. This heads have the cations. This heads, this particular tile have anion, or in some cases and vice versa. So surfactants act as a solubilizing agent. In some of the places, some solute particles are not able to dissolve in the given solvent. In those places, these surfactants play very well as a vehicle and help the solute particles to dissolve in the given solvent. The surfactants act as a solubilizing agent at higher HLB values, that is hydrophile lipophile balance values, that is above 15, and thus enhance the solubility of poorly soluble drugs. Wherever the drugs are poorly soluble, the surfactants are working as a carrier and helping them to make soluble. Okay, as seen here in the picture, it clearly shows that one side is the head side, another one is tail side. That is, one side is hydrophobic portion and downside is the hydrophilic portion. Okay, so this is the concept of surfactants which are helping for the solubility of the drug in the poorly soluble aqueous nature, some of the places. Okay. Okay, the next, solubility of solids and liquids. What are the applications? It is applications are huge. So particularly this is in pharmaceutical industry, in pharmaceutical dosage forms like syrups, elixirs and parenteral are prepared by dissolving solid drugs in suitable solvents. Dissolution is essential for better absorption of drugs. And another point is solubility of a compound serve as a standard test for purity. Of course, it is very much useful for to check the purity, and the solubility principles are used to establish the physicochemical properties of various drugs. So these are the main important applications of solubility of solids in liquids. Okay.